What's up? Welcome to Deconstructing Science. This is my first video, so a little bit about myself. My name is Evelyn, and I'm in school for naturopathic medicine. And for those of you who don't know, we like to use a lot of non-invasive lifestyle changes as our primary modalities to achieve health, and that's going to include things like nutrition, exercise, sleep, stress management, things like that. Being in my fourth year and seeing patients, I really wanted to look at the research myself. I see a lot of different prominent doctors or organizations that have a specific opinion about a topic, and then they have their list of research that backs up that opinion. But then I see a lot of research at the same time from people with opposing opinions. So, what I would like to do in this channel is pick a question at a time and look at research on both sides as unbiased as possible and come up with an educated conclusion on that particular topic. The reason I'm doing this in video format is one, so that I can actually force myself to do it since I have a specific project. Number two, I think being able to explain my reasoning and my thought process is going to make me understand it a lot better. Number three, putting my thought process out in the open is also going to give other people an opportunity to tell me if I'm wrong, and that's going to allow me to also get better. And number four, and my one non-selfish reason, is that maybe someone will find it useful. Before we can look at actual research, we need to lay some groundwork on what science is and some of the problems with science and research in the health field. Science is the study of the structure and function of the natural world around us. And the method that we use to study the world around us is the scientific method, which has a specific order of operations. First, you have to make an observation. Then you ask a question based on that. Then you come up with a hypothesis. And then you, you make a prediction based on that hypothesis. And then you test that prediction through an experiment. And this is very important. And the results of the experiment can either support or reject your hypothesis. If it supports your hypothesis, that's great, but you still need to repeat the same experiment many times by different teams. And if you accumulate enough evidence, experimental evidence, that supports your hypothesis, then you can say that your hypothesis is probably correct. So it's important to remember this concept of needing an experiment in order to support or reject a hypothesis. So when it comes to research, I'm sure that anyone that has had a research class before knows this idea that correlation is not the same as causation. And this is very important to keep in mind because it doesn't matter how tightly two things are correlated, you can never, never, never imply that there's a causal relationship there. What's interesting is that if two things are not correlated at all, that they don't match, then it is very unlikely that there is a causal relationship. So the non-correlation is almost more powerful than the correlation itself. You can actually look up some really funny correlations online, and you'll get things like increased consumption of ice cream is correlated with increased incidence in murders. Therefore, increased consumption of ice cream causes murder, which is ridiculous. But it goes to show that just because two things are correlated, it doesn't mean that one causes the other. So how do you show causation? So typically you do this, like we said, in the scientific method through experimentation. In the field of health, this usually implies something like a randomized controlled trial where you're controlling for variables and intervening. Now, most of the research in the health field is not this type of research. It's actually research that are mostly about looking at correlations or associations. There's this thing called the Bradford-Hill criteria that was developed around the 60s to try to establish causation through correlation, which, as we talked about, is not possible. I'm just going to go through it. I don't think this is a very good criteria, but it exists, so we need to be aware of it. There's 9 criteria. Number one is strength of association. Just like we said, doesn't matter how strongly something is associated, this is not causation. Number two is consistency. This is the idea that the same correlation exists in different parts of the world, but through different populations. And again, it doesn't matter how much tightly something is correlated, you can never imply causation. Number three, specificity. This is a weird one. It's the idea that it's much more likely for something to be causal if A causes only B versus if A causes all these different other things. That's a little bit close-minded. We know, for example, that something that can potentially disrupt the endocrine system can result in many different manifestations with many different symptoms. You can take hypothyroidism, for example. If you do something to disrupt the thyroid, there's all these different symptoms associated with it, but they don't always manifest in every single person. So you can have one person here with constipation, one person over here with hair loss, another person with fatigue, another person with weight gain, and they're all caused by something that disrupted the thyroid. So it's a little bit close-minded. I don't particularly like that criteria at all. Number three, temporality. This one actually makes sense. For A to cause B, A must have happened before B. Yes, definitely. However, just because something happened before something else, it doesn't mean it's causal. Number five, biological gradient. This refers to a dose dependence. So if there's an increase in A, then the increase in incidence of B is also going to occur. And that, again, there's things that are very tightly correlated like that have no relationship, and they're very obviously not related. So again, not a very good criteria. Number six is plausibility. This is the idea that for something to be more likely to be causal, your explanation of how A causes B needs to be congruent with the known science. This is good in the sense that if your explanation clearly goes against known biochemical mechanisms, then I would say you're probably incorrect. However, just because you don't have a mechanism, I don't think it's okay to dismiss it, because that would imply that we already know everything, and we don't. Number seven, coherence. This is very similar to number six. I don't know whether they're two different criteria because it sounds exactly the same. Number eight, experiment. This is the only one where if it's the appropriate experiment, you could actually be showing a causal relationship. Number nine, analogy. This is the idea that if you already have evidence of A causing B, and your new hypothesis is that something similar to A is causing something similar to B in a similar mechanism, then you should accept weaker evidence for that causal relationship. I disagree with that. I think that if that exists, that may make me more likely to want to explore that path and experiment through that idea versus another that maybe doesn't make as much sense. But I would still require the same level of evidence to show that particular causal relationship as I did with any other. I don't think we should be accepted a lower quality evidence. So let's talk about the hierarchy of evidence. It is basically the different types of studies that are typically used in the health science, and they're organized from weakest evidence to strongest evidence. So I have a few problems with this pyramid. So starting with the bottom rung, expert opinion. This is not evidence. This is a logical fallacy called an appeal to authority. If you had to take action in a field that you didn't know much about, and you wanted to consult an expert and take their word in order to take action, that is completely reasonable and understandable. But it is not scientific evidence. And people fall into this all the time. They cite different organizations, they cite prominent doctors, they cite book writers, and their opinion as if it was evidence. It's not. When you're trying to find the truth, an opinion is not evidence. About that, there's the case reports, which is basically a documented anecdote. A doctor has an interesting case that is unique, and they write it up, and that's a case report. Above that, you have case control studies, which is an observational type of study. So you have two groups, one that had a higher incidence of cardiovascular disease and one that didn't. And then you look back in time at whatever it is that you may think is the cause, for example, smoking, and you look at the incidence of smoking in one group versus the other and the incidence of disease. And you basically looking at correlations between these two things. It's pretty low on the totem pole because a lot of the time you're looking back in time at data which may not be very accurate, and there's also a lot of confounding variables that you're not controlling for. The cohort studies are similar to the case control, but they actually follow the two groups. So it allows you to do maybe a little more testing over time, to track their diet in different ways or track whatever it is that you're trying to track a little bit more accurately. But again, you're just really looking at associations. You're not really intervening, or it's not experimental. It's observational. So these two types of studies can't really show a causal relationship. Now, about that is a randomized control trial. This is the only one of these that is an actual experiment. Remember that the scientific method said that you need an experiment to either support or reject your hypothesis. So randomized controlled trials, you're actually intervening. You have two groups. Uh, you control for as many variables as possible, and then you intervene with your treatment, and then you compare the results. So these types of studies are more common in the pharmaceutical realm. It's a little bit more difficult to do with nutrition or other lifestyle changes because for practical reasons, financial reasons, and depending on what it is, potentially ethical reasons. The last two, the systematic review and meta-analysis, is a little bit misleading that they are at the top of the pyramid. So a systematic review is you get a selection of studies about a particular question and you go through them, you analyze them, and you come up with a potentially a new conclusion. And this is basically what I'm doing in this channel. It's going to be a video format of our systematic review. And a meta-analysis is you get a selection of studies, but you actually pull out the raw data from each of these studies and you combine them and you reanalyze them and you come up with new results and then new conclusions. So the reason this is misleading is that the quality of these two types of studies depend on the source material. A meta-analysis of a bunch of case reports are not going to be as good as a well done randomized controlled trial. People like to use the word meta-analysis to back up whatever claim they have, but it can be very misleading. It's important to understand that the quality of a meta-analysis depends on the source material, and the word meta-analysis does not inherently mean that this particular piece of research is worth anything. So I know I've been very negative about science, but I think it's very important to understand its limitations. So one last thing, there's this guy whose name I'm not going to pronounce. He researches research, and he wrote this paper called The Problems with Research in Health. And it's a really interesting read. There's a lot of math and statistics that you can skip over and just read the conclusion. I mean, if you're really into the statistics and the math, and you would like to look at that and tell me if it's actually good, please go ahead. So what I wanted to show you is this particular chart. Particularly the side on the right, the PPV is the positive predictive value, and it's the probability that the association found in a specific piece of research is actually a true association. And as you guys can see, only the top two, the randomized control trial and the meta-analysis on a randomized control trial, actually have a higher likelihood that the association found is a true one versus a false one. So all the other ones, the cohorts, the case reports, everything else, the chances are that the association found is actually false. That's incorrect. So what this tells me is that unless you're looking at those two top types of research, everything else is pretty much worthless. So that's all I really wanted to cover in this video. I know it's been negative, but I think it's really important to understand that science is a tool that was created by humans, and just like us, science also has flaws and limitations. It's a great tool when used properly, but it's not always the right tool for every problem. You know, I'm hoping to find some really good research through this whole endeavor that I can use to make clinical decisions, but we have to understand the limitations of the existing science. And there's other ways to make decisions too. You know, you have just your clinical experience, you have the things that your mentors taught you. There's a lot of different kinds of interventions that are very low risk that make sense. That why not try if there's not immediate danger? There's also just common sense. So yeah, so that's it for today. And in my next video, I'm probably going to choose a question or a topic that doesn't have much research on it, because I wanted to spend some time going over how I'm going to look at the research study, how I'm going to select my studies, and just touch on a few different parts of it. And it'll be more of a demo of what future videos are going to be like. So anyway, thanks for watching, and that's it.